Hello, my name is Lawrence and welcome to my project Inventorious, a real-time grocery shelf manager. I created this project because food waste has been a prominent issue. Once visiting a supermarket, I noticed um, fresh, intact produce left curbside and eventually going to waste. And after research, I learned that almost 1,000 million tons of food waste occur annually, many of which end up in landfill and contributes to global warming. Economically, it's also a major toll on North American economy. Some current solutions exist, fortunately, and that includes supplier-producer communication, which is the sharing of supplier market information with farmers so that they can import the number of items correctly. There's charitable sales, many of which implement through online means. And one example is the Too Good to Go, which allows users to buy secondhand food at a lower price. The Singaporean company Trax also implements computer vision to manage supermarket stock, and all these current solutions together inspired the creation of my project, which aims to solve this problem by making supermarket stock more transparent. Users can see their available options and update the stock information for their communities, while retailers can understand consumer preferences and import their products accordingly. This is how I organized my application. There's a stores page in which the information of the inventory is available. The camera function helps users to update inventory information, and the computer vision engine helps recognizes objects and returning the count of objects. The wishlist page exists for planning purposes, and the profile page includes the user's information. Here's the flow of the stores page. Navigating through the store, a user can extract an item's most recent photo with the item's count. Alternatively, they can find the same item by typing it in the search bar. And this is how it looks in the actual user interface. Navigating through the store, you find item information or the alternative route. Here's the wish list page. A user adds in an item that they want to buy, or a supplier can plan their import by searching for the product, selecting the store, and confirming the numbers. And here is the user interface for wishlist. Lastly, the camera function is embedded in the items page of the store's flow. So after taking a photo, the computer vision engine will count the item and recognize it and update all these information on the review page. And this updated information will be shared among all users to view. So after taking a photo, YOLO V5 detects and counts it, update this data into Firebase, which is the backend database of this whole application, and updating that onto the page. As seen, apples have changed from 26 to 24. Now I want to share a little bit about my development process. And the key feature computer vision model is developed using Python. A user inputs an image and the model outputs the object in its counts. I use the library YOLO V5, and this algorithm divides a given image into grids, performs pooling to extract dominant features, and calculates expected probabilities for the pictured item being a certain item. And it repeats this process and outputs an output after non-maximum suppression, which prevents false positive identifications. And this model runs on a server that's created using Python Flask. The database is where I store all these information, which are the photo of the item, the number of a certain item, and user information. And this uses Firebase. Lastly, the whole mobile app uh, is presented using Flutter, for which I use the programming language Dart. Here's an example of a code snippet. When a user edits a wishlist item, the stock of the item can be updated, and how many of the item the user wants is also constantly modified. As a result of this continuous nature, these two pieces of information are synchronous, and so it requires real-time updates. The stream builder here serves this purpose and treats these real-time data as streams. And since these data are stored in Firebase, it takes a stream that constantly requests a snapshot of the wish list in the Firebase. The builder creates the UI, and it default returns loading text when checking stream snapshot data. If the snapshot data is erroneous, an error message will be returned. Otherwise, the builder does further checks. If the user has already had a wishlist quantity for the item in the designated store, the builder builds the page with the item stock, which is retrieved in another stream builder, and the user's wishlist quantity, which will be updated by constantly undergoing the same checks as the user edits. If not, the builder default returns the item stock as zero, as the user's wishlist quantity for users to edit in the future. To test the effectiveness of this application, I've done several experiments, and the first one concerns precision, recall, and general intersectional reunion. As seen in this image, with um, a decent bounding of items, the which is 50% of intersectional reunion, the precision will be over 60%, which is much higher than the overall precision of the model, 40%. However, the recall of this model is pretty high, about 80%, and that means this model identifies the relevant image items that I trained it with. I've also done a qualitative investigation on uh, the pictures that a user would take, and as shown by the apples and cokes, this model works best on large scale, well angled, and high resolution photos. The second experiment concerns the speed of computer vision model. And I used the timeit module in Python to achieve this. The model is trained on 200 epochs and detects 60 and tested on a sample of 60 images. The mean execution time is about 0.79 seconds with 0.23 standard deviation, which means that the quick speed of this model is quite consistent. Based on this result, we can conclude that this model is easy to use and that fits people's fast paced modern lifestyle. This is important because this ensures the user friendliness of this application, which eventually will help increase the popularity of the app. However, there's certainly future works that I would do for this to further improve this project, and that is mainly about improving the computer vision. One part of it is the vocabulary of items, and this is one of the difficulties that I encountered when developing this project. So, in a supermarket, there's thousands of variations or kinds of products, and it is almost impossible to maintain a high accuracy for all of them uh, while able to while being able to recognize all of them. And so for the current model groups many similar products under a same category, one same category. And so in the future, it will be helpful to increase the vocabulary for more specifically for each product, so that the numbers in this application will be more targeted. The second part will be increasing precision, and I'm planning to do it mainly through image handling, which includes image ratification and panoramic stitching. These are techniques that the Singaporean company Trax employs in their computer vision model. And lastly, expanding the scope of training data will improve the model's capacity, because um, being exposed to more images will allow the model to account for them when running through the computer vision algorithm. That's all for my project. Thank you so much for joining me.